You are most welcome to the second episode of our topic electrostatics, and great kwesiga mote. The notes I'm using were formulated by Onyate Justin Edmond, so we give him the credit for the wonderful notes that we have chosen to use throughout the topic of electrostatics. And today in this episode, we're looking at the Coulomb's law of electrostatics, which states that the force between any 2-point charges is proportional directly to the product of the magnitude of the charges and inversely proportional to the square of the distance of separation of the charges. So when you have two charges, one is charge Q1 and the other one is of magnitude Q2. You don't want to mind about the sign of the charges. They might be opposite, they might be similar charges. If they are opposite, you'll get an attractive force between them, and if they are like charges, you'll get a repulsive force between them. Now we are interested in the magnitude of this force. Now this force will be proportional directly to the product of these charges and will be inversely proportional to the square of their distance of separation. The distance is in meters and the charges are in coulombs. Now, if we remove the constant of proportionality, we get Q1, Q2 out of R squared times a constant. That is, if we have removed the symbol of proportionality and replaced it with the constant of proportionality. Now, the value of this K, if the charges are positioned in air or in a vacuum, it is given by 1 out of 4 pi epsilon naught. And the SI unit of this constant is meters per farad. Now, 1, 4 pi, those are common constants, but epsilon naught is a specific constant and depends on the medium in which the charges are placed. And if they are placed in a vacuum or to a good approximation in air, the value of epsilon naught is 8.85 times 10 power negative 12 farad per meter. In calculations, we can, especially in a vacuum or in air, of course, this epsilon naught is a constant and is called the permittivity of free space. The permittivity of free space. Now, when dealing with calculation, it is common practice for us to use 9 times 10 exponential 9, to use the numerical constant 1 over 4 pi epsilon naught. We replace it with numeric value 9 exponential 9 to shorten and to simplify calculations. We are going to do some examples that involve this law, this Coulomb's law of electrostatics, and we are starting with example 1. Find the force between 2-point charges of positive 4 microcoulombs and negative 3 microcoulombs placed 10 centimeters apart. In this case, our R is 10 centimeters, which is 0.1 meters. Our Q1 is 4 times 10 power negative 6. Micro stands for times 10 power negative 6. Then our Q2 is 3 times 10 power negative 6 coulombs. So the force is given by 9 exponential 9, which is the numerical value of 1 over 4 pi epsilon naught Q1 Q2 over R squared. We substitute the values that we have and we get the force as 10.8 newtons. And it's an attractive force because the force is supposed to have both direction and magnitude. So in this case, since they are unlike charges, the force is attractive. Question number 2, we have 3-point charges which are placed at points A, B, and C as shown on the diagram. At point A, we have a charge of negative 3 microcoulombs. At point B, we have a charge of positive 4 microcoulombs. And at C, we have a charge of negative 7 microcoulombs. We are asked to find the resultant force at B. Now, why are we calling this a resultant force? Because the positive 4 microcoulomb charge will be attracted towards the negative 3 microcoulomb charge, and at the same time will be attracted to the negative 7 microcoulomb charge. So it will be pulled on both sides, and in the end, it will move towards the stronger force, and therefore that's what we call a resultant force. So, of course, we have to convert all our distances into meters. So 10 centimeters becomes a 0.1 meter, and 5 centimeter becomes a 0.05 meters. The force on B due to the charge at A is good by substituting the corresponding values into the formula. F is equal to Q1 Q2 over 4 pi epsilon naught R squared. So this one is 1 over 4 pi epsilon naught 9 to the power 9. Then these are the two charges. This is the charge at B and the charge at A. Then we divide by the square of 0.1 and we get the answer as 10.8. That is the force on A on B due to the charge at A. Then we have the force on B due to the charge at C. When we substitute the magnitude of the charges and the distance, we get 108, but this time it is being pulled towards C because it's an attractive force. The charge at B is pulled towards the charge at C. Here the charge at B was being pulled towards the charge at A. Now, the one towards the right is stronger, or is bigger, is a stronger force than the one towards the left. So we shall subtract to get the resultant force, which is 90 newtons, and the net attraction is towards C. Number 3, we have skipped the introduction part, but we have 3 charges A, B, and C on a straight line with those magnitudes and with the shown distances, and we are asked to calculate the force on the negative 3 microcoulomb charge as it was. Still, we shall do the same. We shall convert these distances into meters. We have 0.02 meters. We have 0.04 meters. Now, what happens to this? We want to find the charge on the 3 microcoulomb. The 2 microcoulomb is positive at A. It will attract the negative 3 microcoulomb. So this is the force at A. It's attractive. Then the negative 4 microcoulomb will push away the negative 3 microcoulomb. It is being pushed away. It is a pushing force. It's a repulsive force because they are like charges. That becomes the force due to C. So both forces are pointing towards the left, are trying to push the negative 3 microcoulomb to move leftward. Our formula still comes in. Electrostatic force, the Coulomb's law is Q1 Q2 out of 4 pi epsilon naught r squared. Then we substitute in all the values of the charges. Note that in these questions, we are not substituting the sign of the charges because the law talked about the product of the magnitude of charges. So irrespective of the signs of the charges, for us, we substitute into our formulae, we put there just the magnitude of the charges. So here we get 135 newtons as Fa, which is towards the left, is being attracted toward the positive 3 microcoulomb. Then Fc, upon substituting charge at C, charge at B, and the distance 0.04, we get 67.5 newtons. Is towards the left because it's being pushed away. Is a repulsive force. So in the end, since they are all pointing towards the left, we are going to actually add the two up. We add the two forces and they give us a total of 202.5 newtons, and it is towards the left. We go to question number 4. Question number 4 is also almost the same as question number 3. They are saying, find the resultant force acting at P if a charge of 1 microcoulomb is placed at that point. Calculate the resultant force acting at point P if a charge of 1 microcoulomb is placed at that point. So here we have a charge of positive 1 microcoulomb that has been placed at point P. Now, let's see what happens. The 2 microcoulomb charge is going to push away, it will be a force of a repulsive force. It's going to push away the positive charge at P. That's why you're seeing force F2 is actually pushing away our positive 1 microcoulomb. Then the same charge at P, since it's positive and the 3 microcoulomb charge is negative, this charge at P will be attracted, pulled towards the negative charge. That's why you're seeing here there is a force F3 and it is acting towards the left. So we have two forces, F3 towards the left, F2 towards the right. Now the resultant will depend on which of the two is a stronger force. Coulomb's law comes in, F is equal to Q1 Q2 out of 4 pi epsilon naught r squared. Then for the force F3, that is due to the 3 microcoulomb charge, we substitute the magnitude of the charge at P, which is 1 microcoulomb, charge at the 3 microcoulomb charge, the 3 times 10 power negative 6. Then we divide the 1 meter. 1 meter starts from here and ends there. The 1 meter is the distance between the 3 microcoulomb charge and the 1 microcoulomb charge, giving us 0.027 newtons towards the left as the arrow was shown. Then F2, that is the force due to the 2 microcoulomb charge. Also, we substitute the corresponding charges and the distance, which is 0.06 this time, between the 2 microcoulomb and the charge P, and we end up getting 0.05 newtons towards the right. So we have two charges, 0.027 and forces, 0.027 newtons towards the left and 0.05 newtons towards the right. Now the 0.05 Newton force is stronger or greater, so we subtract 0.05 minus 0.027, we get 0.027 0.023 newtons, 0.023 newtons, and it is towards the right. Question number five. Question number five. Question number five. We have, please, as we are looking through this video, you'll be pausing this video and you manually carry out the calculations on paper so that your brain can own the working that we are making here. Otherwise, if we just watch casually, it may not work. You watch as you are pausing the video and moving along with the computation, with the calculations. Physics is by doing. It is computation in nature. We can't just watch as if it is a theory lesson. Number five, we are skipping the long introductions because what we actually need is information which can be shown on the diagram. Now this here we have four charges A, B, C, and D placed at four corners of a triangle FD or a square ABC and D of sides 4 centimeters each. And we are required to find the resultant force on the charge placed at the corner of the triangle C. Now, this time, our charge at C, which is positive 3 microcoulomb, is being acted upon by forces due to three different charges. So we shall have to work out all the three different charges, the forces due to all the three different charges. We show their directions and then we work out the resultant of the vector forces. Now, I begin with the charge at D, with how the charge at D affects our charge at C. The charge at D is of positive 5 microcoulomb. The charge at C is of positive 3 microcoulomb. These are like charges, so the positive 5 microcoulomb will push away the 3 microcoulomb with the force Fd. So the force Fd is a repulsive force. Positive 5 microcoulomb is pushing away the positive 3 microcoulomb. And the same thing is happening with the positive 8 microcoulomb. It's also pushing away the charge at C because they are like charges. That's why you're seeing that FB is pointing upwards. Now, we have another force, another charge, negative 4 microcoulomb. It is opposite to the charge at C, which is positive. So we expect this charge to be pulled towards. We expect the 3 microcoulomb charge to be pulled towards the negative 4 microcoulomb since it's an attractive force. Now, next step, we're going to work out the magnitudes of these charges. We have seen the directions, now we need the magnitudes of these specific charges. Before we do that, for the negative 4 microcoulomb, we need to look for the straight distance between point C and point A. Now we need to look for distance CA. Now distance CA is got by Pythagoras theorem, where you have a triangle which is right angled and isosceles at the same time with sides 4, 4. You work out the hypotenuse of that triangle or the longest side using Pythagoras theorem, and it proves to be 5.66 centimeters. However, I would encourage that we can leave our answers in third form to avoid errors due to rounding off. You can leave your answer as root 32 centimeters and proceed that way. But it's the return is still okay. Or if you choose to use decimal, let them be at least 3 decimal places. Then we have got the value of x. Now later on we shall need to resolve or to break down the force Fa in two components, horizontal and vertical, because for vectors they are pointing in different directions which are not parallel. We have to resolve those forces into their vertical and horizontal components, and then we find the vector resultant. So in view that we shall need the angle theta, we find it earlier here. Tan theta is, this theta is the angle there. It is opposite over adjacent, and it gives us 45 degrees. Now using the law of electrostatics, it is here in the formula form. F, the force is equal to the product of the magnitude of the charges Q1, Q2 over 4 pi epsilon naught R squared. I'll be replacing 1 over 4 pi epsilon naught with 9 times 10 power 9, which is its numeric value. So let's look at Fa. Fa we said is the force. Fa we said is the force due to the charge at A. The charge is positive, is 4 times 10 power negative 6, that is Q at A. Q at C is 3 times 10 power negative 6. 9 times 10 power 9 is 1 over 4 pi epsilon naught, then over the square of the distance. This one gives us 33.75 newtons. We do the same thing for the force at B and for the force at D. We get 135 newtons upwards and 184.375 newtons towards the right. Kindly pause the video and work through those calculations yourself. It is very important. Now, after doing this, we are now going to the important aspect of treatment of vector forces, that is finding the resultant through resolving first. Now, when resolving forces, the ones which are already horizontal or vertical needs no breakdown, but the ones which are not horizontal and not vertical are the ones where we shall need to resolve those forces. Let's begin. And we also use the principle that right horizontally, right is positive and right is positive and left is negative. Then vertically we have upwards is positive and downwards is negative. Now we are beginning with the first one. The first force we are looking at is the force F, Fa. Now the Fa has two components. The one which is just next to the angle, adjacent to the angle, takes the cosine. This becomes Fa, the cosine of theta. So the one which is the other side, the horizontal, now becomes, please ensure that you use rulers because vectors are supposed to be done using rulers. Then it becomes automatically Fa, the sine of theta. Remember, our theta is 45. So we can use 45 direct, 45 degrees, and this is 45 degrees. So next we are now going to resolve, write the force as a vector. So the force F, the force F, we look for the horizontal component. Horizontally, Fa, it is facing backwards. Fa sine 45. Fa sine of 45. But it is negative because it is facing backwards. This is Fa, the sine of 45. It's facing backwards. Don't forget always to put the degree symbols. and the angles. Then when we go to FB, FB is entirely vertical, so it has a zero horizontal component. So horizontal is 0 and vertical it is 135. Then when we go to FD is entirely horizontal, so it has, and since it is facing towards the right, it is positive 84.375 as it was got here. Then it has a zero vertical component. It's always important if dealing with a physical quantity to attach its unit. So these are newtons. So when you work that out, we get our components as 60.57 and 111.17. Always pay attention to the trigonometric ratios because sometimes you can make mistakes. Here we are lucky that 45 degrees has the same sign as the cosine. So after getting the two components, which are both positive, we now draw a vector diagram for them. Horizontal is positive towards the right, and the vertical is negative. Sorry, the vertical is also positive. So we draw triangle forces and we indicate. Sometimes I always encourage students, in case maybe it might disturb them changing directions, to always begin with a rectangle. After getting your rectangle, you look at your Fx, the horizontal force. 60.7 means towards the right as it is positive, so both sides which are horizontal, you make them positive. This is 60.57 and this is 60.57 newtons. Then vertically, there it's also positive, also make it positive, and we have 111.17 newtons, 111.17 newtons. Then you check around your rectangle that you have drawn for the corner which has two arrows coming from it. So this corner is this one. So you begin from that corner to draw the resultant force. So this becomes your F magnitude. Then we shall look for the angle between that force we have drawn and the horizontal, which is theta. In this case, we are using alpha, so we're calling it alpha. So we can now find the magnitude using Pythagoras theorem, fx squared plus fy squared. Then you apply the square root, you get 126.59 newtons. Then for the angle, we shall use tan because we have the opposite side and we have the adjacent side. So tan alpha is 111.17 divided by 60.57. When you apply the tan inverse, we get 61.42 degrees. Therefore, the resultant force at C is 126.59 newtons at 61.42 degrees to the horizontal. Let's proceed to example number 6. Example number 6, this time is a triangle, but still we shall work it out using the same idea as number 5. Now this time the triangle has two sides equal, 20 centimeters with isosceles and the base of 10 centimeters. It has the charges A, B, and C as indicated, and they're asking us to find the resultant force at C. Now the charge at C is negative. The charge at A is negative also, which means the charge at A will push away the charge at C. You're seeing that force FA. Force FA, force FA is the resultant force at C due to A is being pushed away. Then B is positive, and at C we have a negative force, which means the negative charge. The the negative charge at C will be attracted towards the positive charge at B. So we have two forces there that are acting on the charge at C. Now, since these forces are not entirely horizontal or vertical, we shall need to break them down or to resolve them into their vertical and horizontal components. Now, to do that one, we shall draw a line parallel to the base of our, enlarge a bit, parallel to the base of our triangle. Because this angle CBA is vertically opposite to this angle here, so these two angles are the same, theta and theta. And because the other angle up is corresponding to the angle at A, which is also theta because this triangle is isosceles. So the other angle becomes theta because they are corresponding angles. As we said before, every force will have two components, horizontal and vertical, but the one next to the angle becomes a cosine. So this, basing on the force FB, this becomes, excuse me, let me reduce this. This becomes F of B, the cos of theta. Then the other one automatically becomes F of B, the sine of theta. We do the same thing for FA. The one next to the angle, the one next to this angle here becomes FA, the cos of theta, and the one which is remaining, the vertical one, now automatically becomes FA, the sine of theta. So since we shall need that angle theta, it is important for us to find it early enough. Now, we have a 10. Now, this altitude we have chopped from the vertex coming downwards. We divide it into two equal parts. So you'll have 5 centimeter here, and you'll have 5 centimeter there. Now, the cos of theta will be adjacent over hypotenuse, 5 out of 20, giving us the angle at 75.5 degrees. Now, let us compute the magnitudes of those charges. Let's begin with FA. Now, FA is the force at C due to the charge at A. Charge at A is positive 5, is negative 5 microcoulomb, but we use its magnitude here, not the sign. Then the charge at C is 3 times 10 power negative 6. Then 1 over 4 pi epsilon naught is 9 times 10 power 9. Then over 0.2 squared, which is 20 centimeters, but in meters. And we get the answer as 3.37 newtons in the shown direction. We do the same for the force due to the charge at B using the corresponding charge 4 microcoulomb times 3 microcoulomb over 0.2 squared, and the constant is 9 times 10 power 9. That one will give us force FB as 2.7 newtons. As we said before, since these two forces are not entirely horizontal or vertical, we are going to consider their components. We have already shown their resolution on the diagram. So, as we said, for the horizontal, whatever is towards the right is positive, whatever is towards the left is negative. For the vertical, whatever is upward is positive, whatever is downward is negative. So, horizontally, we have two forces and they are all towards the right. We have FA cos theta. Theta is 75.5. FA cos theta plus FB the cos of theta. So when we substitute those two, we get 3.375 cos 75.5, and we have 2.7 cos 75.5. Then for the vertical forces, Fs and theta is upward, so it is positive. So Fs and sine of 75 is positive, as you can see it here, is positive. Then the FB sine theta, which is 2.7 sine 75.5, is actually facing downwards. Now, when we do the mathematics there, please don't always forget, I repeat, to indicate the units of these forces. These are physical quantities. So we get that 1.521 and 0.653 newtons. Still, you now represent them on a rectangle forces. Sometimes it is very tricky for students to draw in a triangle, but if you can indicate horizontal, positive, vertical, negative. Then you connect the two to get the resultant force. That's the force at C. So using Pythagoras theorem, we get the force magnitude of 1.655. Then getting the angle alpha using tan inverse of opposite over adjacent, we get 23.23 degrees. And we conclude by saying, therefore, the resultant force at C is 1.655 newtons at 23.23 degrees to the horizontal. We now go to question number 7. Question number 7. Question number 7 is a rectangle, and on the corners of this rectangle, they have applied their charges and they are all positive. So this question number 7 is exactly the same in terms of the working. You can follow the working for question number 4. Question number 5. So you will first question number 5 and follow and work out question number 7. I'm leaving it for the learner to work out question number 7 because it follows. The only unique thing that we shall meet here is this time we shall have a negative y. After resolving everything, we shall get a negative y, fy, and our forces will be like this. Still, you work out the same way, you get the resultant force and the angle it makes. Also have question number 8. Let's move together through question number 8. Question number 8 says 2-point charges A and B, of negative 17.6 microcoulombs and negative 9.0 microcoulomb respectively are placed in a vacuum at a distance of 21 centimeters apart. When a third charge C is placed midway between A and B, the net force on B is 0. Roman 1. Determine the charge on C. Then Roman 2. Sketch the electric field lines for the above charge distribution. We shall look at the electric field lines later when we're looking at electric fields, but for now we shall devote ourselves to Roman 1, which involves the Coulomb's law of electrostatics. Now, we have two charges. One is negative 17 microcoulomb placed at A. The other is negative 9 microcoulomb placed at B. Now, automatically, the negative 17 microcoulomb charge will repel the negative 9 microcoulomb charge with a force that is calculated, that is force due to A, force due to the charge at A. Because we want the net force, we need the net force acting on B to be 0. So the charge at A will repel the charge at B. This is a repulsive force towards the ray. towards the right. So we work it out using Coulomb's law. That force is there. We haven't got out the exact numerical value because we are still using it in the calculation. So now we go. For us, if since this force is acting towards the right, then for the net force on B to be zero, the charge at C must be an opposite charge to the charge at B so that it can attract or pull it back. So charge at Q, which we don't know, must be a positive charge, positive Q. And it will pull B back to the left. So this one is actually leftward. So assuming the charge at Q has magnitude Q, which we don't know. So when we figure in the values of the charge at C, which is 9 to the 10 power negative 6, this is the constant or 4 pi epsilon naught. This is the unknown charge at C. Then this one should be equal and opposite, plus of course the distance. Since it is the midpoint, it is half of 21, which is 10.5 centimeters, which translates to 0.105 meters. So these two, since they are equal and opposite, for them to cancel and give us a net force as 0, just equate the two. Now you work out the value of the charge Q as 4.4 times 10 power negative 6 micro Coulomb. We go to question number 9. Two pith balls P and Q, each of mass 0.1 grams, are separately suspended from this one is what is from the same point by threads that are long. When the balls are given equal charges, they repel each other and come to rest 18 centimeters apart. Find the magnitude of each charge. Now, in this question, we have two pith balls, each having a mass of 0.1 grams. They are held by threads, equal threads, and since they have charge and the charge is the same, they will repel because they are given equal charges. They will repel. They will repel themselves and be at a distance. Now, the distance between them, when they come to rest, is 18 centimeters apart. They are asking us to find the magnitude of each charge. So let those charges be QQ, as shown on the diagram. We have Q and Q. They are distance of 18 centimeters apart. So by the time they come to rest, we assume that the strings are making an angle theta with the downward vertical. So it is 30 centimeters. Now each of these masses will have a weight mg. Will have a weight mg, and since they are being supported by the string, so the strings will be having tension. So we have tension T in the strings. What is keeping them apart is the electrostatic force, which we are showing by F, a force of repulsion, pushing them from one another. Now, we shall need to resolve these forces so that we can balance the forces at each individual charge. So if we consider one of the charges, let's say at Q, we have the electrostatic force, we have the weight, and the tension T in the string. Since it's on the tension which is not vertical, we shall resolve it. Now to resolve it, we need to find the angle theta. Now the angle theta we are using, half of 18 is 9 centimeters, 30. So we shall use the sine of theta is 9 out of 30, opposite over hypotenuse, and we get the angle theta as 17.5 degrees. Next, what we do is we look for there's the components of the tension T. Now, since this is theta, the angle theta, that vertical angle is theta, the alternate angle or the opposite angle here is also theta. So this part of the force tension which is next to the angle takes the cosine and the other automatically takes the sine. So we have T sine theta and then T cos theta. Now when we try to resolve the process vertically, we discover that T cos theta is equal to the weight mg. They have to balance for them to be in equilibrium. Then T cos of cos theta is 17.5. So we substitute it there and we get the value of the tension as 10.029 times 10.3. Now, when we resolve the forces horizontally, we get T sine theta towards the left is equal to the electrostatic force towards the right. So we substitute the values. The Q we don't have it, so we leave it unknown. Then we have the distance between the charges is 18 centimeters, which is 0.18 meters squared. We put the value of the constant. We have the value of sin theta as 9 over 30. We have what the Gauss tension up there. So we substitute those values and we get the charge Q as 3.3 times 10 to the power negative 8 coulombs. Now, I am leaving the next question, because it's similar question number 9. I am leaving question number 10 for the learner to try. You can pause the question, you can pause the video and you copy down the question number 10 and you try it out. Then you also proceed. Solution is here. You can compare with the solution, or if you're stuck, you can still pass through it. Then afterwards, you proceed and attempt this exercise. Good enough, it has its answers in brackets. There are a total of 5 questions that will help you to consolidate whatever we have been able to discuss under Coulomb's law of electrostatics. I remind Bright Okwesi Gamote and I encourage you to like this video, share, and please subscribe to the channel. Watch out for the next episode, which will be electric fields, where we shall be looking at electric field intensity and we calculate its values. So please endure not to miss the next episode that we're going to look at. Thank you.